dun sa previous na na meetings para ma-minimize natin yung error between yung actual na value at saka yung training data set, yung hypothesis from the training data set. Gumagamit tayo ng gradient descent. So, ang gradient descent is just one of the several optimization na algorithms para nga ma-minimize yung error na yun. Okay? Um, Ito yung mga common na ginagamit na optimization algorithms. So, we have gradient descent, stochastic gradient descent, mini-batch stochastic gradient descent, stochastic gradient descent with momentum, Nesterov accelerated gradient, adaptive gradient, ADA, adaptive delta, RMS prop, at saka ADAM. Okay, i-describe ko lang briefly kung ano tong mga iba't ibang optimization algorithms na to in terms of yung mathematical treatment or mathematical equations. Okay, and then of course describe din natin kung ano yung magandang gamitin, depende sa kung anong klaseng dataset yung meron ka. Dito sa slide na to, ang makikita ninyo ay yung iba't ibang speeds nung mga algorithms. Okay? So, for example, yung kulay pula dito sa upper figure, yung kulay pula is SGD. Okay, and makikita nyo yung kulay pula dito, stochastic gradient descent, sunod doon. Okay. Medyo mabagal siya kumpara. Siya yung pinakamabagal kumpara dun sa ibang mga algorithms. You have momentum here, okay, yung kulay green. Okay, so mabilis siya pero once it's near the optimum value, mabagal na rin yung approach niya. Okay, we have NAG, Nesterov accelerated gradient, which is similar to momentum. Okay, then ADA grad, yung kulay blue, okay, ADA delta, yung kulay dilaw, at yung RMS prop, yung kulay itim. Okay, so it seems na halos sabay-sabay lang sila dumating except for yung stochastic gradient descent, of course. Okay, yun siya yung pinakamabagal. Pero the rest ay halos sabay-sabay lang dumating sa optimum in terms of speed. In terms of accuracy, yung ADA grad, yung pinakamabilis na ma-achieve yung accuracy in terms of the number of epochs. Okay. So itong x-axis dito is number of epochs. And yung kulay pula, stochastic gradient descent, it requires several more epochs bago ka dumating dun sa mataas na accuracy. Okay, so ito yung mga advantages at disadvantages. Makikita nyo na kaagad mula dito sa figure na ito. Okay, let's begin with gradient descent. We already know what gradient descent is. Ito yung ginamit natin before, and yung basic equation ng gradient descent is this. So basically, we're summing over all the data set. So we're determining remember this term here is the gradient. And we're determining the gradient from all of the data set kasi sinasum natin lahat ng values ng data set. Okay, and if we do that, then we can get this cost function, okay, which decreases with the number of epochs quite fast, diba? Depende rin sa number of data set. And yung gradient descent actually figures out yung path let's say, quite quickly, okay, because it uses the whole data set. Ang disadvantage nito is that because it uses the whole data set, once you have a data set that's really, really large, okay, syempre babagal ngayon yung pag-compute kasi it has to compute for the gradient for the whole data set for each iteration. Okay, which means that yung computation time will be longer. Since it also solves for diba, ito yung mga weights, diba, or yung features, it will also solve this for each iteration. So in addition to solving for the gradient, hahanapin niya rin yung weights or yung features in each iteration. So so makikita nyo kung gaano kabagal yung pag-compute. Okay, and well, sa mga previous example natin, sa linear regression, for example, sa single feature na linear regression, we have just two weights or two features. Dun sa multivariate linear regression, we have 5, 6, 7 features or 5, 6, 7 weights, diba? And that's easy enough to compute. But pagdating sa mga images, when you try to classify images, this method will not work as fast simply because yung weights na i-compute nyo doon consist of hundred thousands to millions of features or millions of weights. Okay, so that means that the computation time will be much, much longer. Now, the way to improve on this computation time is to use this stochastic gradient descent. Now, kung titignan niyo mabuti, nawala yung summation notation dito because you're not summing over all the data sets sa stochastic gradient descent. Okay, you're just taking the gradient with respect to one instance. Okay, so which means this makes it faster kasi tignan mo lang kung ano yung data set ng isang data point lang, isang instance. Kunin mo yung gradient from that data point and then you immediately solve yung weights, okay, yung features. Okay, and naturally this is much faster. However, because you're solving only for one instance, okay, or one data point, oftentimes yung direction na tinuturo ng gradient is not the optimum path. Okay, so kaya nangyayari is dahil nga isang instance tinuturo ka niya in a direction that's not a direct path towards the minimum value. Okay, so mangyayari is sa first instance ganito yung lalabas. Okay, sa second instance, biglang mapupunta dito yung direction, third instance dito, and so on and so forth. So meron siyang random na parang movement just because it's taking the gradient over one instance lang. Okay, even though it looks like it doesn't look like a direct path, it's still much faster kumpara sa gradient descent simply because hindi ka nagsasum over all the data set. Okay, so ang isa pang pampabilis dito, okay, I mean pampa-increase ng efficiency sa computation is itong learning rate. Previously sa gradient descent, yung learning rate, we set it at a fixed value. To improve yung stochastic gradient descent na method, we introduce what's called a learning schedule. So, ibig sabihin, binavary natin yung learning rate based sa number of iterations. So, halimbawa, after several iterations, after 100 iterations, okay, baguhin natin yung learning rate to this one. Okay, after another several hundred iterations, babaguhin natin yung learning rate to this one. So merong schedule nung learning rate. Okay. And that makes things a bit faster, and ang isa pang advantage niyan is it doesn't get stuck dun sa isang local na minimum. Okay, of course, another advantage is yung memory requirements since you're just summing over a small data set, di ba? Is a single value lang per each iteration. Okay, ang disadvantage dito is matagal mag-converge and yun nga, it can get stuck to a local minima if you don't create a learning schedule for the learning rate. Okay, so nakita nyo naman yun dun sa unang figure, di ba kanina? Okay, na mabagal yung kulay pula dito, mabagal yung pagdating niya dun sa optimum value at it takes a certain number of epochs until it reaches dito sa maximum value ng accuracy. Okay, so yun ang stochastic gradient descent. Sorry, narinig niyo pala yung pag-sip na. Now, one way to improve that is to do what's called a mini batch gradient descent. So pag mini batch gradient descent, you're summing, nakikita nyo na nabalik yung summation sign, but you're not going to sum over just one instance. You're just going to sum over a few instances. Like say, for example lang, sampung data sets at a time, sampung data points at a time, or 32 or 64, yung ganon na number. Okay, so which means na since you're not summing over the whole data set, okay, you're just summing over sections or portions of the data set. Mas mabilis siya ng konti kumpara sa stochastic, sa single instance na stochastic gradient descent. So pag mini batch, okay, ganito yung magiging behavior niya. Okay, so makikita nyo na hindi siya ganun ka-random. Okay, mas directed ng konti towards the minimum value. Okay, and mas mabilis yung pag-compute niya kumpara sa stochastic gradient descent. Of course, mas mabagal pa rin to or mas mabilis pa rin to kumpara sa mas mabagal pa rin to kumpara sa gradient descent for small data, pero for large data, for large number of data sets, itong mini batch gradient descent is more efficient kumpara sa gradient descent. Okay, ang problema lang dito is medyo noisy yung yung cost function. Okay, for mini batch gradient descent. The same as stochastic gradients. Dito hindi nakalagay yun. Okay, so noisy pa rin siya kumpara sa gradient descent na malinis yung cost function. Okay. So dito medyo erratic yung learning rates, which makes it a little bit hard pagdating sa interpretation ng model. Okay, kung maayos yung model niyo or hindi. Okay, another problem is it can also get stuck at the local minima, similar to just stochastic gradient descent. Okay, so again, you still to avoid that or to try to avoid that, papalitan nyo itong or naglalagay kayo ng learning schedule, okay, for the learning rate. Okay, the next, well, ito basically yung technique. So, ang gagawin mo kung meron kang ganitong dataset, i-randomize mo siya. So, yung column 1, column 2, column n, m-1, column m, i-randomize nyo muna tong columns na ito. Okay? Pagkatapos yung ma-randomize, yung same randomization gagawin nyo rin dun sa labels. Okay? Pagkatapos niyan, kukuha kayo for example ng 64 training examples, then you solve for the gradient base dito sa first 64, and then you update. Okay, i-update nyo itong weights na ito. Okay, then 64 ulit, update, 64 ulit, update. Okay, 64 ulit, update. And of course, hindi naman yan lahat exactly multiples of 64, di ba? So ito less than 64 na to, tapos update. Okay, once you do that, that's one epoch. Okay, isang epoch lang yan. Okay. So yun yung tinatawag na Yun yung ibig sabihin ng epoch dito. Okay, so eto ngayon ang tawag natin dito sa iteration. So this one iteration, second iteration, first iteration to compute for the gradient descent and to update. Second iteration to compute for the gradient descent and update. Third iteration to compute for the gradient descent, update, and so on and so forth. Then once na makuha niyo lahat ng training set, yun yung isang epoch. Okay? Okay. So yun yung method ng mini batch gradient descent. Now, yung ibang optimization algorithms has this formulas, these equations. So na-discuss natin yung stochastic gradient descent, and dito para lang mas maintindihan niyo, so dito we're taking the gradient of the cost function with respect to a single instance. Okay? Sa mini batch gradient descent, we're taking the gradient of the cost function with respect to a batch of instances. So B here means one batch. Like in this example, B, one batch is 64. Now, sa stochastic gradient descent with momentum, meron kayong sinusolve na vector dito, which is the momentum, which is called the momentum vector. Okay, and that momentum vector will be your gradient. Okay. So, dun sa unang iteration, makukuha niyo yung momentum vector. This is of course zero, or sometimes it has an initial value. Tapos i-add niyo siya dun sa ordinary na gradient descent. Tapos multiply niyo by the learning rate. Yan yung bago ninyo na momentum vector. Yun yung ipapasok niyo dito sa equation ngayon para ma-update yung weights or yung features. Okay, and then for the next iteration, you also you use the previous momentum to get the new momentum. Then syempre i-add nyo dun sa previous momentum, multiply nyo by some constant. I-add nyo yun dun sa gradient descent times the learning rate. Okay, so yun yung stochastic gradient descent with momentum. So the momentum with this technique, of course, it has all the advantages of stochastic gradient descent, and it converges faster kumpara sa gradient descent na algorithm. Dito sa Nesterov accelerated gradient, okay, ang difference dito is that dito, itong cost function, you subtract the weights, okay, from the momentum vector. Okay, so instead of just getting the new momentum from the previous momentum, okay, and then adding it to the gradient, first of all, kukunin nyo muna yung gradient, okay, base sa previous na momentum. Okay. Tapos, i-multiply nyo yan by the learning rate, and then i-add nyo yan dun sa momentum din ng previous na iteration para makuha yung bagong momentum. So, ito lang yung difference between NAG at saka SGDM. Okay? And then you use this new momentum to update yung weights. Okay, obviously makikita nyo na pareho lang yung effect nito. Of course, this is just a more efficient method kasi it already yung weights ninyo already points, or because you're adding the momentum dun sa weight pa lang, pinopoint niya na kaagad dun sa tamang direction yung gradient. Okay, so this is by doing this, you get a more efficient way of going to solving for the minimum value. Okay, now there's also this optimization algorithm called adaptive gradient descent. Okay, this is just a stochastic gradient update for every parameter theta at each time step. Okay, and this is how the update works. So ito yung gradient nyo. This is the normal gradient descent na alam natin. Okay, yun yung GTI dito. Then you have this learning rate. Tapos, meron kayo nitong tawag dito, itong update na to. Gradient update. Okay, this gradient update, sandali. Okay, is applied dito sa mga weights na ito. And okay. So yun, so yung learning rate nyo actually is sort of divided dito sa o dinidivide nyo pa yung learning rate with this gradient update. Okay, which also makes it a bit more efficient. Hindi mo na kailangang i-update yung learning rate manually, okay, kumpara sa kung dito ka sa stochastic gradient descent. Dito, kailangan mo i-code pa ito eh. Kailangan nyo i-code muna itong alpha para magkaroon ka ng learning schedule. But in this case, ito na mismo yung equation na gagamitin nyo, and you don't need the learning rate kumpara sa stochastic gradient descent. So the adaptive gradient basically adapts based on the gradient at each iteration or at each instance. Okay, or at each batch. Okay, depende kung anong ginagawa niyo. Now, ang ADA delta is quite similar dun sa ADA grad. Okay, except ang difference lang is this. Okay, so you have this equation, okay, for the learning rate. Okay, at yung equation na yun is obtained by solving this parameter. So remember, this is the gradient, and then you have 1 minus gamma times this one, which is initially set to 1 or 0, and then this parameter here, which is set around 0.9. Okay, so na-optimize na itong value na to 0.9. So ito yung equation that will allow you to compute for the learning rate for each iteration. Okay. And then you also have RMS prop. Halos wala siyang difference dun sa ADA grad. Okay, ang difference niya lang is itong beta value, I think. Okay, so yung beta, pareho lang naman yung equation na ito dito. And then the beta, I think you can change. And then you have ADAM, or adaptive moment estimation, okay, which is RMS prop with momentum. Okay, so if you recall, yung momentum is also computed, okay, dito from here. So you add the term to the gradient para makukuha, which will act as the momentum, which will make it faster to determine yung optimum direction, not just the magnitude. So lahat ng mga ito ay yun yung mga iba't ibang optimization algorithms. Now, how do you know which algorithm to choose? Okay. So, kung titignan nyo rito sa graph, ang pinaka-problema kasi dito is some algorithms, when it reaches a saddle point, pwede siyang hindi niya mahahanap yung optimum value. Okay. So dito sa saddle point, alam niyo naman ang saddle point is meron kayong, in one direction may minimum value siya, pero in another direction actually it's a maximum value. Okay, so for stochastic gradient descent, momentum and NAG, okay, ma-reach niya tong optimum value na to, but this is not a global minimum but a local minimum. Okay. So diyan magaling yung SGD momentum at saka NAG. Ang ADA grad, okay, will simply ADA grad, ADA delta at saka RMS prop, and NAG pala, ayan yung kulay violet. Will still try to find yung global na minimum. Okay, so anong gagawin niyo ngayon? Anong rules, shall we say, para piliin yung isang algorithm? So it is observed that the SGD algorithm is stuck at a saddle point, tulad na nakikita natin dito. So SGD algorithm can only be used for shallow networks. Okay, ano ibig sabihin ng shallow networks? Mamaya i-discuss natin yung neural networks. And sa neural networks, if you have a single hidden layer, or single or one or two or three, okay, or actually one or two lang, then you call that a shallow network. Okay, if you have one hidden layer. Okay, but if you have multiple ang tawag dito, hidden layers, then it's no longer a shallow network, it's a deep neural network, so DNN. Okay, and for deep neural networks, you never use stochastic gradient descent. Okay, otherwise you get stuck at a saddle point. All the other algorithms except stochastic gradient descent finally converges one after the other, ADL delta being the fastest, followed by momentum algorithm. Okay, so makikita naman natin yung dito na yung kulay dilaw, ADA delta, siya yung pinakamabilis na mag-converge. Okay. ADA grad and ADA delta algorithm can be used for sparse data. Okay. So, i-explain ko mamaya kung ano yung sparse data. Momentum and NAG work well for most cases but is slower. So siguro for smaller data sets, you can use momentum and Nesterov accelerated gradient. Animation for Adam is not available, but from the plot, yung animation dito, wala dito yung Adam. It is observed that it is the fastest algorithm to converge to minima. Ang ibig sabihin dito, ang plot is yun dito. Yan. Ay, wala rin pala siya dito. Okay, anyway. So, yan. And then, Adam is considered the best algorithm amongst all the algorithm discussed above. So, kung ayaw nyo na mag-isip, then just choose Adam. Okay. Now, ano ibig sabihin ng sparse data? So, this is an example of sparse data. So, kung meron kayong variable na kung saan masyadong mataas yung percentage ng data na walang laman, like in this example, kikita niyo sensors 3 to 11, wala namang data na pinoprovide. Yung sensor 1 even has this 0 values, di ba? Sensor 2, ganun din. So, this is called the sparse data. So, yung ADA grad and ADA delta is good to use pagdating sa mga sparse na data. Okay, so for example, sa mga weather prediction, di ba? Sa weather prediction, hindi ka naman nagkakaroon ng weather disturbances all throughout the year, right? Meron kang weather disturbances at specific dates of the year lang, and then the rest of the time wala kang data set, walang storm. Okay, so that can be considered as a sparse data depende kung paano mo ipo-process. Okay, and ito nga yung isang other example is itong mga sensors na ito, like yung mga weather sensors, when you detect when you sense pressure, temperature, wind velocity, wind direction. Diba? Sometimes wala talagang hangin, so wala kang wind velocity. Okay, yung anemometer mo naka-point lang in a specific direction, so walang change. So ganun yung mga pwedeng mapagkunan or pwedeng paghugutan ng mga sparse na data. Okay, so ito yung mga examples ng ito yung mga iba't ibang optimization algorithms which you can use in place of the gradient descent. Oftentimes, you never use or hindi mo talaga ginagamit itong gradient descent. Okay, kadalasan itong SGD na yung ginagamit ninyo, yun nga for shallow networks. And if you don't want to think about it, you just choose Adam. And then pag meron kayong sparse data, then you can use ADA grad or ADA delta.